uh, coordinates of a vector with respect to another basis. Let V be a finite dimensional vector space over the field K, where K is the field of real numbers or the field of complex numbers. Firstly, a definition, an order set of vectors B, vectors V1, V2 up to Vn is an ordered basis of V of our vector space V if it satisfies the following two conditions. Firstly, V B spans V, that is, V is the set of all the linear combinations of these vectors, that is, the vectors of the form alpha 1 V1 plus alpha 2 V2 plus so on plus alpha n Vn, where the coefficients alpha k are from the field of scalars k. And the second condition, B is a linearly independent set of vectors, that is, such a linear combination alpha 1 V1 plus alpha 2 V2 plus alpha n Vn can be zero only in the case when all the coefficients are zero. Alpha 1 equals alpha 2 equals so on equals alpha n, all the coefficients are zero. So, remark, if B is an ordered basis, if B is an ordered basis of V, then from the first condition it follows that for any vector x from V, there exist the scalars, let us denote them by x1, x2 up to xn, such that x can be written as x1 v1 plus x2 v2 plus xn vn. Any element of our vector space has such a form. And secondly, any x can be expressed in a unique way in this form. The coefficients are uniquely determined. The coefficients x1, x2, xn of x are uniquely determined. If we suppose that x can be written in two ways in this form, that x1 v1 plus x2 v2 plus xn vn, and also let us x1 prime v1 plus x2 prime v2 plus so on plus xn prime vn. Then this relation can also be written as x1 minus x1 prime times v1 plus x2 minus x2 prime v2 plus so on xn minus xn prime vn equals 0. But from the second condition, it follows that all the coefficients must be 0. That is, we must have x1 minus x1 prime equals 0, x2 minus x2 prime equals 0, so on, xn minus xn prime equals 0, but that is x1 equals x1 prime. From this we get x2 equals x2 prime, and so on. From the last relation, xn prime equals xn equals xn prime. So the representation of a vector as a linear combination of the vectors of the considered basis is unique. The coefficients are uniquely determined. The coefficients are called x1, x2, and so on, up to xn, are the coordinates of x with respect to the considered basis B coordinates of the considered vectors with respect with the considered basis. We have considered an ordered basis. So the order of the vectors is the indicated order: first vector, second vector, last vector. So to any x from V, it corresponds the system of the coefficients x1, x2 up to xn, an element of kn of this vector space. Where K n is the space of all the elements of the form alpha 1, alpha 2, alpha n with alpha 1, alpha 2, alpha n scalars from the field K. This has a structure, a vector space over K, the addition by components, also multiplication by components. Now, alternatively, the Kn can be regarded as the space of column matrices Kn, an alternative representation as the set of all the column matrices, and in this case it is useful to use the superscript instead of subscripts, alpha 1, alpha 2, up to alpha n, where again alpha 1, alpha 2, alpha n are scalars from K. Kn here is the space of all these matrices. And this notation, this way to describe Kn is useful when we take into consideration the change of the basis we use in order to describe our vector space. So by using this representation, so a vector space, a vector from V, a vector x can be represented as x equals, if we use this notation, and we denote the coordinates by using a superscript x1, v1 plus x2, v2 plus so on, plus xn, vn. Or we can write this in the following way: a sum for k from 1 up to n, xk, vk, a simpler notation, a simpler way to write this is x equals, we do not write this symbol, and we write just x equals xk vk, where by xk vk we understand exactly this expression x1 v1 plus x2 v2 plus xn vn. This is Einstein summation convention. We simplify the notation, especially in the case of tensors, where we have several subscripts, and when we have a product and we have the same a subscript of one factor coincides to a subscript of another factor, we understand that we have a sum with respect to k. K takes values from 1 up to n. So this is instead of this. So we do not write this symbol. We understand this. We shall use this short notation, and let us consider for our vector space two bases. And the following definition. Let be v1, v2 up to vn, and b prime equals, we know that in the case of a vector space, a finite dimensional vector space, any two bases have the same number of vectors, v1 prime, v2 prime, up to vn prime. Two bases for our vector space, and in order to distinguish them, this the old basis of V, and the second basis the new basis of V. Each of them is a basis of V, so any vector from V can be written as a linear combination of these vectors. And for example, the vectors, we consider each vector of the second basis, and we write it as a linear combination. V1 prime, let be alpha 1, 1, v1 plus alpha 1, 2, v2 plus so on, plus alpha 1 n vn. Then the second vector v2 prime equals alpha 2, 1 v1 plus alpha 2 v2 plus so on, plus alpha to n vn, and the last vector vn prime equals alpha n1 v1 plus alpha n2 v2 plus alpha nn vn. The vectors of the new basis expressed in terms of the vectors of the old basis. If we use this convention, we can write all this relation in the following way: Vj, j is arbitrary from 1 to Vj prime equals alpha j k vk. Here we have a product, so we have here a sum with respect to k. K takes values from 1 up to n. This is a shorter notation for this set of relations where j goes from 1 up to n. By using these coefficients, we form the following matrix S. Let us denote by S. On the first column, we put the coefficients of V1 prime. So alpha 1, 1, alpha 1, 2, alpha up to alpha 1, n. On the second column, we put the coefficients of the next vector. So we'll have alpha to 1, alpha, and up to alpha n, n, and so on. The last column, the coefficients of Vn prime. So alpha n1, alpha n2, up to alpha nn. This is called the change of basis matrix from the old basis B to B prime. Change of basis matrix. In a very similar way, we can express the vectors of the old basis in terms of the vectors of the new basis, and we get another matrix. We prove that it is exactly the inverse of S. So now, with the same notation, the following theorem. The inverse matrix S minus 1, we denote the elements here by beta, beta 1, 1, beta 1, 2, up to beta 1, and the second column beta 2, 1, beta, up to beta 2n. The last column beta n1, beta n2, up to beta nn. The inverse matrix of S satisfying the relations alpha, alpha j k beta k m equals delta jm. Here we have a sum with respect to k, and the relation beta k j alpha j m equals delta km. We have here a sum with respect to j. and here the vectors of the old basis vk equals beta k j v prime j. These relations here, this symbol where delta, where delta jm equals 1 for j equals m, and 0 for j different from m. The inverse matrix satisfying this relation is exactly the change of basis matrix from B prime, the old, the new basis to B proof. So we have this relation, and the coefficients alpha. We have V prime j equals, we have introduced alpha as the coefficients of the expansion of the vectors of the new basis in terms of the old basis. Now, this relation, but we can continue here. We insert this, and we get alpha jk. Instead of vk, we put beta instead of vk, beta k, and here we have to put a different j is fixed here times v prime. We use this instead of vk, but this instead of j we use m. And you can see here that we have equality, the same vector expressed in terms of the new basis in two ways, but we know that the coefficients are uniquely determined from this. The coefficient of Vm from the right hand side, Vm prime, must be the same as the coefficient from the left hand side. So this alpha j k beta k m must be we have here just one vector, so this must be 1 for m equals j, and 0 for m different from j. We have here j is fixed to just one vector, and here m we have a sum with respect to m, but only the coefficient of v prime j when m is j is 1. All the other coefficients here are 0. You can, for example, here we can write this as delta jm v prime m. Here is a sum with respect to m, and This is different from 0 and only when m takes the value j. So this expression is here is exactly the same. And now if we identify the coefficients of v prime m, this coefficient, this is this symbol is exactly delta delta jm is 1 for m equals j and different from. So we have exactly. So this is the relation alpha, alpha j is the first relation. And if you can see that the obtained relation alpha j k beta km equals delta jm. Here j and m are fixed, and we have a sum with respect to k. For fixed m, this is on a line, on the line m of S minus of this matrix, and here is on the column, so beta line the multiplication of the matrices. This is from this we get that S minus this matrix. Let us denote for the moment the as t. From this we get that t times S is exactly the identity matrix, the matrix which has 1 on the main diagonal and all of the other elements are 0. The elements of this matrix are exactly delta jm. We have 1 when j equals m and 0. Now, in a very similar way, we can prove the second relation. And we can see that similarly we get that S times T is also the unit matrix. And so from these two relations, we get that indeed T is S minus 1. S minus 1, and the elements of this matrix are the coefficients we have used in order to express the vectors of the basis in terms of the new basis. So we have this result. And now the change of coordinates of a vector the following theorem with these notations. Let us consider again the two bases and we have denoted the relations between vectors Vj prime. We have denoted can be written in the following y j k dk and bk is beta k j v prime j. And now let us consider an arbitrary vector x, the coordinates with respect to the old basis, expansion in terms of the old basis, x k vk, and the same vector, the expansion in terms with respect to the new basis, x prime j v prime j. And from this we get that the old coordinates xk xk is alpha kj, the relation between the old coordinates and the new coordinates, jx prime j and x prime j equals beta j kxk. For example, these are the new coordinates in terms of the old ones. And this relation, the second relation, for example, here for j goes to 1 up to n, x prime 1, x prime 2, up to x prime n. And here we have here the old coordinates, x1, x2, up to xn. And here x prime 1 is beta 1 multiplied by x1 so let us beta 1, 2, and so on up to beta n 1. This is this relation. We have here a sum with respect to k. So when j is 1, we have this multiplied by this plus this multiplied by this plus the last multiplied by this and so on, beta 1n, beta nn. So we get this is exactly s minus 1. This matrix is s minus 1. But let us prove this. Proof. We start from this relation. For example, x k v k equals x prime j v j prime. And we substitute, for example, here by using this relation, and we get x prime j, and instead of this v prime j, we put alpha j k vk. And these vectors, we have here the same vector expressed in terms of the old basis to expressions. We know that the coefficients must be the same, so the coefficient of vk from the left-hand side must be the same as the coefficient from the right-hand side, and from this we get that xk is indeed, here is a multiplication of two numbers. We can change the order. It is alpha jk multiplied by x prime j. sum with respect to j, that is this formula. In a very similar way, we can obtain the second to express in a very, very similar way. So by using the change of basis matrix, we can compute the coordinates in a new basis if we know the coordinates in the old basis, or conversely. Thank you.